speak about signature-based models, in particular signatures. It's an object that I find extremely fascinating with a lot of nice properties, which has a bit of a cost in order to enter and to understand and to appreciate it. But actually, as soon as one spends some time to understand it, one can see that it's not as difficult as it looks at the first sight, and is extremely interesting, as I already said. For this reason, I will spend some time at the beginning really to introduce what this is, what is the signature. Then now we hear from many different perspectives and many different people in our field. And after, I will show you a couple of ways we used to exploit these properties. And yes, this is more or less the way that I will follow tonight. So why, wait, that I need to move a bit the faces, otherwise I cannot see my own slides. Okay. Why do we like signatures? We like signature for two reasons, mainly. The first one, because the time-extended signature of a continuous semi-martingale uniquely determines its path. It means that is an object that you can use instead of using the whole path of your semi-martingale, okay? So all the information are contained there in the signature. On the other hand, because every polynomial on the signature has a linear representative, you can transform every polynomial in something linear, which is much easier and much nicer. If you combine these two properties, you arrive already at some very interesting summarizing property, here a bit heuristically. If you have a quantity that you can write as a continuous map of the trajectory, of the whole trajectory of your semi-martingale, then it can be written as a continuous map of the signature, since the information on the trajectory is contained also in the signature. Continuous map can be approximated by polynomials. Polynomials can be written as linear map. You get an approximation of the quantity you are interested in terms of a linear function of the signature. Okay, something very complicated, something much more interesting a priori. Okay, here L is a linear map, and X we put the hat if we want to consider not just the signature of X itself, but X together with time. We will always consider the signature of X together with time. Why is a linear map interesting? Because with linear maps we have many. With linearity, we can recover many interesting properties. For example, linear regressions is something that now nowadays is optimized in a way that is very difficult to imagine something more quick. Because we can recover property that require, for example, coefficients to be affine, to be polynomial, because all of that is a special case of a linear map. So we can, so the contrary, if you as a condition ask something to be polynomial, this is in particular satisfied if this object is linear. So all the nice representation that we get from this word can still be applied for the signature. And also many other things that we will see also tonight. This from a very high perspective. And now, before continuing, we need first to define what it is, step by step. I start with a trajectory that is nice. You can imagine it to be a very nice, smooth function, something that you know very well and do not present any issue of any type. Okay, what is the signature? It's a sequence, where in the sequence we say at space the space 0, just the constant function 1. Then you get the integral of constant with respect to the past. If x is smooth, you can imagine this as its derivative dt, okay? Then you consider the double integral. You obtain the object that you get here, and you integrate once again, and then once again, and then once again. And so you have a sequence where you store all the integral one after each other. Okay. A couple of observations. In which type of space could this live? Well, you need to save a spot for each integral. So a spot for level 0, a spot for level 1, a spot for level 2, and so on. So sequence space. Typically, you save it in this way, and typically you denote it in this way, and you call it extended tensor algebra. You can say, why should we introduce some new notation for it? Well, in one dimension, you would not need it, but in more dimension, it gets a bit more complicated. We also need a notation in order to access those integrals, okay? So we have the signature and we want to take the kth iterated integral. How do we do? Well, we do like this. We take E1 E1 k times, pair it with the bracket, with the signature, to select the kth iterated integral of the signature. To select the one, the very first one, we choose E empty set. Okay, it's not the only notation that we use. We can also, instead of writing one after each other, we can write it with exponential or with a vector, like here. In this capital I, we can save who we integrated with respect to who and for how many times. So in this case, we integrate the one and only component again and again with respect to itself, k times. Okay? With the bracket, we access the component of the signature. Okay. We can define it term by term, or we can define it recursively. So if we have the single integral, the double integral is just given by the previous one, integrated again with respect to our path of final variation. Okay? And the triple one will be the integral of the second one, integrated again with respect to the path of final variation. So we can say directly kth iterated integral, or we can define it in a recursive way. There is one important observation that we need to do. Here we do not see what is the initial condition of our path. Since here we always differentiate, if we shift x by a constant, we will never see the constant. So with the signature, we can characterize the trajectory up to constant shifts. If it's constantly move up or down, you cannot see. Good to keep in mind. Now, summarizing what is in one dimension, the signature of a one-dimensional path of finite variation takes value in the extended tensor algebra and is an object of this form, where every element is defined as the element before integrated with respect to the path. Okay, till here everything okay. Now we move to D dimension. Also, in this case, we consider a very nice path with all the properties that you can imagine. So very smooth, very nice, no problem of any sort. What is the signature? Same thing. A collection of iterated integral, one iterated integral, double integrated integral, triple integrated integral, and so on. Of what? Of every component with respect to every component. So you get the one that is always there in front of them. Simple integrals with respect to the first component till with respect to the D component. Double integral, you start by integrating the first component and then again the first, and then you continue the integrated first with respect to the first component and then with respect to the second, and so on. You save all of them, every possible iterated integral. Okay. Now, fine, the space get a bit more involved. Why? Because of level 1, we have D of them. At level 2, we have D square of them. Level 3, we have D cube. So the space is not very flat anymore. At level 0, we have just one element. At level 1, we have D elements. At level 2, D square. And so the extended tensor algebra here is a bit more, it's a bit more visible why we need a structure in the sense of this one, which just says we have a sequence where in every element we save how many spots as we need in order to save our iterated integrals. Okay. Now, notation. We do need to access components of the signature. We do it exactly as before. We save in a vector I, I1, In, which are the components of our path that we integrate in the order that we specify, which means if we take this component of the signature, we are taking the ith one element of the path, integrated with respect to the I2, integrated with respect to the I3, and so on, till with respect to the component In of our path. We are just taking note of who we integrated with respect to who and in which order. We cannot switch. We obtain something different. This is also important. Okay? So, a way to access the signature. For example, just to see, if we have a process which is two-dimensional, and we want to compute the element 1, 2 of the signature, we get the integral of 1 with respect to the first component, which is y, integrated with respect to the second component, which is z, which is, the first integral can be computed explicitly, is ys minus y0, integrated with respect to zs. Okay? This is just to give you an example of what would be this component of the signature. We can also define it recursively, exactly as we did before. If we want to integrate I1 till IN, we can stop one integral before the end, take that element of the signature, which will be this one, and then integrate with respect to the component IN. For example, in this case, we can take this one inside. This is the component 1 of the signature, and we integrate with respect to the second component, recursively. This permits us to write the definition in a more compact form. What is the signature in the dimension? We have all the elements written like this, starting from empty set, E1, ED, 1, 1, 1, 2, and so on till DD, and then you go to the triple levels and so on, where the first element is 1, everybody else can be written as the component of the signature without the last index, integrated with respect to the last index. Iterative index. We are just speaking about iterative index. Now, next step. We move from very beautiful path of finite variation to semi-martingale, continuous still for the moment. What does it change? Till here, nothing. Till here, nothing. What changes here? We need to integrate, not in Riemann-Stieltjes sense, but in Stratonovich sense. Okay, so iterated integral in Stratonovich sense. What is Stratonovich? If you're familiar with Ito, which is something that in finance we are much more used to, is Ito plus a correction in terms of the quadratic variation. Okay, and you can say, why Stratonovich? I always thought that I would have never used Stratonovich in my life. Correct. Well, we can, there is a question. Okay. It's that I cannot see the Zoom bar anymore.
I don't see it. No.
Maybe it's there. Could one use Ito formulation? Yes, one can. And in one of the two projects that I will show you tonight, we will use it. But with Ito formulation, the property that I'm about to show you does not hold or is more complicated. Okay. Why do we want Stratonovich? We want Stratonovich because Stratonovich satisfies integration by part. If you multiply two of them, so two semi-martingale, you get the integral of the first with respect to the second plus the second with respect to the first. Give me a second that I turn on the light. I underestimated that here is getting dark. Okay, and this is very nice. Why? Because or we can even see directly from here. Yt, if you now imagine that y0 and z0 are equal to 0, yt is signature of level 1, yz is signature of level 1. The two of them together, multiplied, is a polynomial in the signature. You are multiplying two components. Instead, what you have here is a signature of level 2, a linear one. And what you have here is a signature of level 2, again a linear one. So this relation is between a polynomial in the signature and a linear map in the signature. Okay. We can also do it more generally, and we get exactly this. If we take the product of these two processes, we can apply the integration by parts that you have here, and you get the integral of the first with respect to the second plus the integral of the second with respect to the first. You apply the definition. You know that the J component of the signature can be written as the component of the signature without the last element, integrated with respect to the last element, and the same here. So if this again can be written in linear form, we can conclude that if we multiply so by induction, if we multiply two elements of the signature, we get a linear combination of the signature. Now, the linear combination is given by this, that corresponds exactly to what is written here, but can still look a bit abstract. We can see it by means of example that I think that clarify it a lot. Take component 1 of the signature and you square it. Component 1 is 1 integrated with respect to x, right? So it's xt minus x0. We take x0 equal to 0, so it's just xt. You square it. You apply the formula, and you get 2 times integral of x with respect to x plus quadratic variation. What is this? It's exactly 2 times the Stratonovich integral, which is 2 times component 2 of the signature, because this is 1 integrated with respect to x, integrated with respect to x. Here we have a polynomial of degree 2, here we have a polynomial of degree 1. Okay? 2 times E1 times E1 is exactly the so-called shuffle product between E1 and itself. Okay. We can do also with 2 different components. What is this? This is component 1, this is component 2. Multiply together because they are 2 signature elements of level 1. You apply the formula, you get integral of x1 with respect to x2 plus the integral of x2 with respect to x1 plus quadratic variation. Again, you can split this quadratic variation in half. You give half of the quadratic variation to this and half of the quadratic variation to this, and you get exactly the sum of the 2 Stratonovich integral, which correspond to what? The signature at level, the signature 1, 2, and the signature 2, 1, like this. So you can see that the product of 2 linear components of the signature give you a linear combination of the signature. What is the combination? Is the sum of these 2 that corresponds to the shuffle product of E1 and 2. And so on. You can continue as much as you want. Some of them are very interesting. If you take just one component to the power k, then you can write it as, so the shuffle product is exactly k factorial 1111 k times. And so you can conclude that if, since this one is xt, on the left-hand side we have xt to the power k, and this is the element 1111 of the signature. So if you have just one component, then if you have just one dimension, then the kth element of the signature is just the power k divided by k factorial, like a Taylor basis. Okay, this is an interesting thing. So if x is one-dimensional, what you get is a Taylor basis. Okay. Going back to the question, if we use Ito, this is not so direct because we have the quadratic variation here, which is annoying and cannot always be written as linear combination of the signature. In some cases, yes. For example, if you want to consider the signature of a Brownian motion together with time, then it's fine, because every time that you reach this type of term of the Brownian motion, this can be written as something that depends on the Brownian motion dt, and t can be seen as the first component of the process given by time in Brownian motion of which you are computing the signature. You can do it, it's more delicate. If you want the shuffle, you should stick to Stratonovich. The Stratonovich signature satisfies the shuffle property, and one says that lies in the group, which is a subset of the extended tensor algebra. Okay. Some examples to see what we have. If xt is just t, the identity, then it's one-dimensional, we get the Taylor basis. Okay, all the Taylor basis. This is a process that depends on t. For every t, we have the sequence of all the Taylor bases in t. if X is a one-dimensional continuous semi-martingale with X0 equal to 0, we get exactly the same, just that instead of T, we have Xt. And you can say, okay, but we said that it should characterize the trajectory. Here we do not see anything of the trajectory because this is T and this just depends on Xt. There is no dependence on what X did between time 0 and time T. Trajectory start to enter when you move to 2 dimension, in particular when you include time. When you include time on top Taylor basis, you also get the integral of S with respect to X and the integral of X with respect to S. And if you go higher in the dimension, you also get many others. Okay? So, in 2 dimension, you get something more than the Taylor basis. But the Taylor basis is always a good reference example, because here you can see, for example, that if you take 2 components and you multiply them together, you get another component multiplied by a constant. You go from a polynomial of degree 2 to a polynomial of degree 1, for example. Uniqueness of the time-extended signature. If we know the signature capital T, we also know all the trajectory of X between time 0 and time T. Why? Because this element here can be written as finite linear combination of the signature. Why? S to the power k divided by k factorial is the component of the signature given by 11111 k times. Because we take the component 1 of the process, which is T, and we integrate it k times. If we do it, we get T to the power k divided by k factorial. Okay. Xi minus Xi times S minus X0 is level 1 signature. This is a multiplication, so of 2 elements of the signature. So we get again a linear combination of the signature, and then we integrate. So we go 1 level higher in the signature, which means that this type of term here is a linear combination of the signature. But now, what do we have? We have that Sk divided by 2. As we can write, we know what is this value. We also know what is the value of Xs minus X0 multiplied by every possible polynomial. Polynomial is dense on 0t. And so we can shrink polynomials till when you get an indicator function, shrink the indicator function to identify what is the value of the process at a specific time s. So knowing this for every k lets you uniquely identify what is your process, xi at any time between 0 and t. This is extremely nice. Why? Because here we were working with the whole trajectory. Here we are working just with capital T, which means that it's true we move to an infinite dimensional object, but in a Markovian sense. Here we can forget everything happened before and just work with the final value. And so we are back in the Markovian case, where there is a world of very nice and powerful properties there ready to use. Okay. Then, one can do more. There is the so-called chain relation, which lets you say, okay, but from time to time, I have a trajectory and I'm interested to separate what happened before a certain time s and what happened after a certain time s. You can do it through the chain relation. The chain relation put in relation the signature between 0 and s and the signature between s of the path starting at time s and continuing in time t. Okay, is given by this one. You sum over all possible indices that, if you concatenate, give you the component of the signature that you are interested in. You can say again, okay, and then what? Well, suppose that you want to compute, for example, a conditional expectation. This is extremely interesting in that type of case, because this just contains information till time s, so it's observable at time s. This concerns the future, so this one can be moved out of the conditional expectation and we can focus on just this part here, that is the increments, just focus on the increments. This will be very useful for our project. For example, maybe this I can do it a bit quickly, or I will still be speaking about the nice properties of the signature at the end of the seminar. For example, suppose that you want to know what is the first component of the signature at time t. You use chain relation and you say, how can I write the word one? The word one I can write as one and nothing, or nothing and one. Okay. So if we write as one and nothing, we get the signature at level, so the first component of the signature till time s, which is 6s minus 60 multiplied by 1. Same here. If we sum the two together, xs simplify, and we get indeed the signature, the one component of the signature between 0 and t. And you can say, okay, well, I did not need chain relation to know that this is the case. What is nice and that this works also for much, much higher order type of iterated integrals, okay? So it's not that the mathematics behind is complicated, it's just that is everything put in the same framework such that you can simplify your computation and not do them by hand, term by term, okay? You can do it for the level 2. How can you write the word 1, 1? You can write as 1, 1, nothing. You can write as 1, 1, or nothing and 1, 1. You compute what is the signature of each element of, like, the signature at level 1, 1 is xs minus 60 squared. Same for this. Here we have just the signature at level 1, so xs minus 60, and same this. This is between s and t, so we have xt minus xs. If you do the computation, you get indeed xt minus 60 squared, which is what you wanted to see. Why is this useful? It's useful because we can compute conditional expectation. And in particular, if the original process X had independent increments, then we can get rid of the filtration and we are back to a standard expectation, which means that we move from something complicated like a conditional expectation to something like a number, okay? And all the randomicity is enclosed in the signature that we take out of the expectation. This will be very useful. Okay. Last property, which is the more complicated one. So all of this signature comes from the world of rough path and these kind of things. So it's a theory that is very beautiful, that contains also some quite complicated results. Till now, we could survive without really using any technique that are just from there. For the universal approximation theory, we need a bit of that. We start from a continuous semi-martingale, very good. We take the signature till level 2, means level 0, level 1, level 2. One simple components and double integrals of t and the process. Then the universal approximation theorem says that if you take a continuous map of the signature till level 2, you can approximate it arbitrarily well on compact set by linear combination of the signature of X. Okay? Lambda I are some numbers that you put in front, so coefficient of the linear combination, and I contains a set of vectors and is finite. What is complicated here is topologies. So you need to understand this is a continuous map of the trajectories, and so you need to understand which kind, what does it mean to be continuous or compact with respect to the topology that you put the set of trajectories. Okay, so I will not enter in detail to that, but is the slightly more, is the more complicated thing, and yeah, this is a very nice and strong result that contains that to be proved needs some properties of the signature that comes indeed from a path and are due to very, very smart people. Okay, now, those are more or less the main properties of the signature. I can show you what we, some of the things that we decided to do in order to have fun with signatures. This was my first work on the signature and is together with Crista Cucchiero and Guido Gazzani. Guido Gazzani is now in Verona. He's an assistant professor, and Crista Cucchiero, I guess that many of you know her. She is a professor in Vienna. We were at the time working all together in Vienna. Okay, what? Wait, I have 2 more comments. Okay. Could you also say a few words about the reparametrization invariance of the signature, you mean? So if I'm interpreting right your question, okay, yes. We get rid, so if you take just the signature alone of a process and you reparameterize the process, you get the same signature. So you cannot distinguish between a process and its reparametrization. You see it very well in one dimension because you just see the process at time t. So it does not matter if you get it quickly there and then you stay, or if you take a lot of time before arriving there. We get rid of all those problems by including time t. If you include time t, you fix a scale. And if you reparameterize, you will not have t anymore here. And so by fixing the first component to be t, you do not have the problem of not distinguishing between reparameterizations. I hope that this helps. So adding time, you get rid of all the problems like tree-like equivalencies, reparameterization, and so on. Okay. Our goal was to get a good model for some traded asset S. What do we mean by good model? We wanted something universal, meaning that we are able to reproduce many behaviors. We want something tractable. So it's nice to be universal, but if you cannot compute anything, then there is no point. And something easy to calibrate. We cannot take 1 month to calibrate our model because otherwise it cannot be used. The main ingredient behind the model was some market's primary process. This is what stays behind the model. And what should it be? It should be something that we can generate easily. And something that is reasonable to assume to be a d-dimensional continuous semi-martingale. So it could also be not continuous, but then in order to get the integration by part, one need to use Marcus integration, which is much more complicated than Stratonovich integration. We worked on that. So, there is my colleague Francesca Primavera, that with her we had a project in order to extend all of these to jumps. So it's possible, but the theory gets much more involved. And X encode all the randomness of our traded asset in a good way, meaning that the paths of S are continuous map of the path of fixed head. For example, what you should imagine? You should imagine like S being the solution of a strong SDE and X being a Brownian motion. Then you can imagine that the randomness of the strong solution of the SDE comes from the Brownian motion, and the Brownian motion is reasonable to be assumed to be a continuous market. Okay, so X should be something nice and easy. S should depend on X, meaning that randomicity comes from X, and the two are related by something continuous. The model that we consider then is just a linear model. Linear combination of the signature of the time extended signature of the primary process X. Linear combination. And what do we have? We have X. This is the signature. We do not take a linear combination of all the elements of the signature, but we stop at a certain depth. This is N. And the parameters of what will be the model are N, which are numbers that we need to decide where to put. As my colleague Nyoatto says, this means that our price could also be negative from time to time. Very true. But this was more, the goal of this model was not to be a model by its own, but to reproduce what other models were used. And also it was a first step. Then we moved to a more sophisticated, more geometrical one. It was not our idea. Something very similar was introduced before by Perez-Ribas Salvinch proof in the 2020. Okay, this is flexible. One can prove that on compacts we can approximate every possible strong solution of SDE, because again, from rough path we know the strong solution are indeed continuous map of the driving noise. So we can approximate them by polynomial, so we can approximate them by inverse. Shortly said. We can guarantee a classical condition like no arbitrage. That's okay. One can do it by checking that the last integral that we have here is with respect to a martingale. Like if you choose X to be a Q martingale, where Q is some pricing measure, equivalent martingale measure, and you check that the last integral that you do with respect to it, and you add the corresponding Stratonovich correction, you can make sure that the model is a local, is a true martingale even, and so you do not have problems of arbitration. You know that this is tractable because the time extended signature of your model can be written as a map of the coefficients and of the signature of the original process. What does it mean? Imagine that here, instead of this, you get your price process and you want to know its moments. Moments are contained in the signature, right? Because the signature contains Taylor basis. So you can write all the moments of your price as a function that depend on the signature of what you use to be your primary process. That can be, for example, a Brownian motion. Okay. In particular, knowing the expected signature, we can compute with respect to the pricing measure. We can compute an approximation, an approximated price of a path-dependent option, because now we can approximate every continuous map of the trajectory by evaluating a polynomial, meaning that we start from the path-dependent option. We write it as linear map of the signature of the price. We go from the signature of the price to the signature of X. We use the fact that we know what is the expected signature. We have a closed form. Okay? This is the signature. Very nice property. Be careful, because this is something that one should say. Approximation is on compacts, not everywhere, on compacts. This can look, this kind of things that us theoretical people like to say, but then at the end nobody cares, but no, it's very important. In particular, because you can say, well, then I can use this in order to calibrate, to choose my L. When you calibrate, the L that will pop up will be very crazy. So in the meantime, now you are looking for L, so you explore and you find some coefficients that do not make sense at all, bringing your trajectory very out of the compact that you considered at the beginning, where you fit your optimization. Okay, so it could be that at the end you are calibrating with something that is not anymore an approximation of what you wanted to fit. Okay, so careful, remember that we are, so if you already calibrated your model and you want to use this for pricing, fine. For calibration, less fine. Question. Isn't the UAT only valid on compact set on the path space? Yes. Is that a limitation for approximation in practice? Yes. So if, it depends what, right? So if you already calibrated and you know where your process will live, not so much, because you can select your compact big enough such that you know with which probability your process will stay in the compact. And so you are just excluding something that happened with a very small probability. You can decide the level of certainty that you want to have for this. It's different if you want to work with different processes, like, for example, during the calibration. In that case, you need to be very careful. For us, for example, we decided not to use this because at the end it was not working in the way we wanted it to work. So you need to keep in mind that this is on compact and to be careful with this. Okay. Now, okay. Formulas for computation of expected signature are available for X sufficiently nice, meaning in particular Markov diffusion. You can get nice formulas for computing the expected signature. If X is a polynomial process, for who of you is familiar with this, or affine processes, then this is even available in closed form. So it's a matrix exponential, the expected signature of the primary. Okay, now we wanted to choose the L. This is the last step, right? So we know that it should be flexible, we know that it should be free of arbitrage, but we need to understand if we can calibrate it quickly. To what we decided to calibrate? To prices of call options. That I guess that you are familiar with, but I still remember what it is. A call option is a contract that if you fix a strike K, pay you the difference between ST and K in the case that as the price at time T is bigger than K. Okay. Its price from a theoretical level is given by the expectation with respect to an equivalent martingale pressure. We are very good in computing expectation, okay, with this, with our model. So even if we will not be very good, the point is that we would like to say we choose L such that the theoretical price of our model that we can compute through the expectation match the prices available on the market. Now there are two ways. Either you approximate this with linear map of the signature, but it's dangerous, and I suggest you not to try it. Or you say, well, our model is a linear model, which means that updating the parameter does not mean a new simulation of the whole process. You can save the signature at time capital T somewhere, and when you update the parameters, you do a scalar product, and by Monte Carlo, you can compute this very quickly and very efficiently. An update of the parameter does not require new simulation, so you just do a scalar multiplication and you get your expectation. So what did we get? Trying to reproduce the surface, the implied volatility surface, which is like, so you take all the prices of the call option for different K and different T, and then you rescale it in a particular way in order to have it a bit more homoscedastic. Almost elastic. If one has this, and if we try to fit the implied volatility, so this price surface of the Aston model, using the signature model truncated at level 3, imposing the no arbitrage condition, which means that we get a 13-dimensional parameter space, then we can reproduce it very well. And we get an error, which is, so you can see it here, very, very, very low. So Aston, no property, no problem at all. We can, even just with this, for us, and this is a model which is much simpler than the true Aston. So it's just the primary process is a 2-dimensional cube Brownian motion, still at 5 minutes, which is an object that we all know very well. Okay, we can reproduce Aston very well. We can also reproduce the S&P 500. And here, you can see that on the shorter maturity, we start to get a bit more error. But here, the truncation is again at level 3. Already, if you go at level 4, you get lower, the error gets lower. I have again a question. My computer refused to open. Okay. Is the equivalent martingale answer for this model? This is not unique for this model. So it's not, I guess, that till when there is just one Brownian motion, it should, for 2 probably not. So we did not investigate much on that. We just take care to not introduce arbitrage. Then, conclusion. we saw that this is an interesting model, not of this part. I still have 3 minutes. I want to show you also.
Also a bit more.
Okay, very good. Yeah, linear model is flexible, we can compute things, and we can calibrate it quickly. So the last part that I wanted to show you, because I think that is also interesting, is a new paper that I have together with Federico Bandi and Roberto Renaud. Roberto Renaud is in ESSEC in Paris, and Federico Bandi is at the Johns Hopkins in Washington. It should be, no, it is in archive since this week. The idea is to try to reach also other type of problems with respect to the one that we consider till now, and move a bit more in the econometric type of work. And consider expansions. The idea is quite simple. You take a process which is an input process. Then you suppose that the processes that you have inside, C0 and C1, are again of Ito form. So something ds, something dw, both of them. W one-dimensional for now, but it can be of the dimension that you want. Okay. So you can plug it in. So instead of C0, you can write C0. Instead of C1, you can write it as C1. Okay. You can do some order. As 0, then you have C0, 0 times T, C1, 0 times Brownian motion. Should use the pen. C1, 0 times Brownian motion. Okay. And everything else are double integrals of time and time, Brownian motion and time, Brownian motion, Brownian motion, Brownian motion. Okay. So linear combination of double integrals. Okay. What do we have here is a linear combination of the signature till level 1 of time and Brownian motion. Here we have double integrals. We can do it again. We can say, okay, suppose that each of them can again be written as something dr, something dw. It's not asking much, right? If you can do it, then you can plug it in. This is what we already got before, linear combination of level 1. And you get also the other terms. So this C000 is inside a double integral with respect to time. C10 is inside a double integral Brownian motion time, and you have the 4 of them. Everything remains as an integral more, which is 1, 2, 3. Each of them is a linear combination of triple integrals. So what do we have? This is a linear combination of the signature till level 2, Ito signature in this case. Okay, and you can do it as many times as you want, which means that you can say, okay, if I can do this n times, at the end, I will have S0 plus linear combination of iterated integrals from level 1 till level n. And whatever remains is iterated integrals of depth n plus 1, which is epsilon n. I call it epsilon n. And why is this nice? Because epsilon n is an error term in many cases of integers. For example, if you take the expectation, you know that Brownian motion go to 0 as the square root of t. So every time that you integrate, at least you go to 0 square root of t quicker. So as more deep you go, as quicker this error then go to 0. So epsilon n behaves like an error term. If you get rid of the epsilon n and you just look at what remains, is linear combination of the signature of the Brownian motion, which is a Markov process, first of all, and is the Brownian motion. We know the Brownian motion, everything about the Brownian motion, right? And is the signature. For the signature, we know how to compute many things, automatically, no? By iterations and these kind of things. And in particular, for example, multiplying 2 of them we obtain again a linear combination of them. If, so, being a Markov process is extremely interesting if you now want to compute the expectation of a function of this ST, because first you get rid of the error term, and then you get the expectation of a function of a Markovian process. So you can do a Markov expansion and get an approximation of any order, without much effort. So you need to imagine that the typical way to do expansion is to compute one term at a time, ito formula again. Let me see, there is a question. Is this an extension of the argument for solution of controlled ODE to SDE? I don't know. I don't know what you are referring to. Is this an extension of the argument for solution of control ODE to SDE? There is no control yet here. We are just approximating a process with, it's like doing an approximation of a continuous map with a polynomial for small times. We are doing Taylor, essentially, but for stochastic processes. I'm not sure that I answered this question. Okay, and what is nice is that one can prove that if one look at the generator of the Markov process given by the signature, it is applied to function of the form function applied to linear combination of the signature, is of a very specific form, is derivatives, where inside there is always the same linear combination multiplied by another linear combination. So at the end, we can, if we put together this type of information, we can code exactly. We just need to code what is B and what is sigma. It's a linear map. So this means now sigma is bilinear and B is linear, which means that B is a matrix and sigma is a cube. You code them and you can apply the generator again in order to get automatically by your computer the expansion of the expectation of a nice map of ST of any order. Till any order maybe is a bit optimistic. When the dimension get too big, then the computer collapses. But still, you get close to the of any order. This is the result. To conclude, now this I would say that we can also this. We go directly to the maybe let me mention this. Together also with Janka Müller, who was another colleague in Vienna, we also, since we are good in computing expectation, we also did a joint calibration of the price and the VIX, writing the VIX as a conditional expectation. And assuming that the primary process is a polynomial, we use the fact that the signature is again a polynomial process, which means that the conditional expectation of the signature, can be computed as a matrix exponential. Why would we care? Because if we write the VIX in this way, what we have inside is a linear combination of the signature, which is a polynomial process. So this conditional expectation can be written as an exponential, a matrix exponential multiplied by the signature of the primary process at time s. So we get a closed form for the VIX, and we can do the calibration. Very good. Now, what else can one do? Can include jumps. This is doable, and one can do both from like more stochastic analysis perspective, like computing moments and these kind of things, and for the expansion, also the expansion workflow. One can study the infinite dimensional object, try to understand if we can compute quantities of the whole process, like really working on an infinite dimensional space. One can use other powerful techniques, like, so we are speaking about Taylor basis. If we consider the whole object, we can consider power series. And if we consider converging power series, we can resource to complex analysis. Like all the results about when a power series converge, things like if a power series converge, maybe also its derivative converge, where and when, and all these kind of things. So a result based on very strong mathematics then can be used in order to increase the thing that one can do with the signature. Same with duality theory from population genetics that give you stochastic representation of solution of SD question. Regarding the jumps can be included. Are you referring to semi-martingales driven by a generality process? Yes, for example, this is if you want to check the universal approximation theory, you can do it. Or the model of which I showed the calibration. You can include as driver also a Levy process. The calibration is more delicate because, of course, you need to decide how to model jumps somehow. But the model and the property of the model still works. Approximation-wise, you need to be careful because polynomials, so moments in the jumps, do not go to zero quickly. Like the Brownian motion, the kth moment of the Brownian motion go to zero quicker than the first moment of the Brownian motion. So as higher is k, as quicker it goes to zero. For a Poisson process, it's not like this. So it's, it's not scaled in the same way, but iterated integrals go to zero quicker and quicker. So as more you integrate, as quicker you go to zero. So you can still get rid of the error term and stay with a Markov process with the jumps. And then write, do the Markov expansion to expand the convolution. Let it here such that I can open it. One can also do more challenging joint calibration, like the VX6, which is an object that I'm still studying, to be very honest, but you can construct it starting from the conditional expectation of the VX, which is a bit challenging because there is the annoying square root here. So you need a smart paper in order to come out of it, because of course the square root is not smooth. One can consider also other type of algebras. Algebras, why do I mean that? Signatures are nice because you multiply two of them and you are still in, so they are algebras. But maybe they are not the smarter one. So when you consider a class of functions which are dense in the continuous function, you can think about polynomials, but maybe there are others that are more, that are smarter for some applications, like Fourier, for example. So something that is maybe also bound and form an algebra. What would be the equivalent thing with the signature? Can we work with something similar? And much more. So now there are really, today I was trying to remember who I could put on this slide, but really there is so many, also like, for example, Sam that was speaking before, he's also working on signature. And I noticed that I did not put on my slide of people that I know work on signature. So there is a lot of people in the UK, in France, in, let's say, the region between Switzerland and Austria, in Germany, between Munich and Berlin, now in Italy also. And yeah, and there are also many people that worked on something that actually was signatures, but were not using the word signature, but getting very nice result from them. Let's just. Okay. Have researchers work with signature for more general random fields?
Maybe Sara, sorry, Sara, because of time constraint. Sorry, I know that you keep getting questions, but maybe let's come to an end so that we can open the platform for everybody for the questions. Okay, so at least we can say thank you.
Thank you.
So thanks a lot. No, it was great that you could answer a question meanwhile, but now I thought, okay, The questions were increasing exponentially at the end. So thanks a lot. It was
Thank you.
great, and also very didactical at the beginning, which is great for people that, like me, have heard talks in signature, but they don't work. So it was really, really great. I have some questions myself, but let me first open the floor to questions from others. So let's see if I can see.
Should I read the question that I got before? Maybe.
Okay, if you still have a question on your chat, because I cannot see the question just sent to you, so of course you can answer that.
Okay, yes. Yeah, it's a special chat, I think. So, have researchers worked with signatures for more general random fields, d-parameter stochastic processes, for example, in connection with SPD? I would appreciate your comment on this topic. Very good question. I know that there were people working on images signature, but in connection with SPD, it could be. So the people working on signature is very big. I'm not, it could be even interesting, but I don't know exactly about it. Okay.
So I don't see raised hands. Maybe I can ask a quick one. We are a bit out of time, but maybe very quick, which is also in general for when I hear talks in signature that, of course, there is a truncation to make it computable. Is there, I don't know, kind of an estimate of a goodness, for example, from synthetic data, right? So is there an estimate of how good of a truncation is according to N, right? So yeah, how long you should go to get the good enough?
It's a very good question. What we typically do is try to see what our computer can do as maximal, and then try to see how far we can push with the flexibility of the model that we consider. I know that some people, like in Paris, were trying to understand like which kind of smart way one can consider. So if there is a smart way,
convergence, right? So
yeah, exactly. If you speak about Stone-Weierstrass, then there is no rate of convergence. You know the distance, but you don't know where. If you speak about Taylor, like small time, then yes, you can estimate what is the error and understand where do you want to truncate. So you know exactly what you lose by truncating. Yes, okay. But in Stone-Weierstrass, up to the thing that I was saying before, that you can estimate the probability of lying in the compact. This, yes. But saying, no, or as far as I know, no, we didn't know.
So maybe quickly, we have 2 raised hands. So if we can have a quick question, quick answer would be amazing. So I think Joseph was first and then Paul.
There are also 2 in the chat and 5 in the other chat.
So Joseph, I think you can unmute yourself.
Thank you, Sarah, for the talk, and hi. About which other algebras did you think about?
Actually, this is something that I was discussing with Paul Hager, my second raised hand. And you can consider if you truncate the signature and then you plug it in, for example, Fourier basis. Then you can still have linear, so the same type of information, because you can truncate at arbitrary level, but work with something that is bounded instead of polynomials.
But this is not point separating.
It depends. It could be.
But if you truncate it, it's never.
Truncated at arbitrary level, not at fixed level.
So you allow every level. Okay. So then you put an algebra into the Fourier basis, but this looks a little bit like over.
Yes, indeed, it makes more sense to plug in the log signature instead of the signature at that point.
Okay. But it's somehow signature based. Not think about something which is different.
No, still signature based. Yes.
Yeah. Okay. Thank you.
Thank you, Joseph. Paul?
Hi, Sara. Thank you very much for this very nice talk. My question was about this. You gave an argument which was referring to this compact set issue for the calibration of your SIG model.
Yes.
So I don't know, could you quickly switch to the slide so I can remember my question better?
Yes, of course. Actually, to be honest, we spent quite some time before realizing that this was a problem.
Ah, okay.
Here.
So if I see, okay, if you approximate it as a function of the signature of S, then I see you have this
Yes.
compact set issue. If you approximate it as a function of signature of X and a function so of L and the signature of X, then the compact set is fixed. So it doesn't depend on L. That's what I want to say.
That does not, yes, right. So you mean if you approximate this directly as a functional of X, but it would depend on S2.
Or I mean, approximate
On L.
like basically like PL, right?
Yeah. Yes.
So did you try this in numerics to approximate f
No.
of S as a function of L and the signature of X?
No, we didn't do it. We were always approximating, like, for example, the shape of the call option, for example.
Right, yeah.
And then this was in terms of the signature of the price, and then writing the signature of the price as the signature of X, and then okay. But I don't, so you mean that one can write this as a function of both L and, it's a smart idea, maybe that could work. Because you say X is always stay where it should stay. And
Yeah,
not,
basically you fix the sample, like you said also, you fix the samples of X. You don't have to resimulate, you just approximate it with these samples, yeah.
But then it means that you are changing the function that you want to approximate with the L.
Yep.
And you want that all the functions have the same error on that compact. So you fix the compact, but then you change the function, so you have the same problem. So,
yeah, I mean,
because
you have to choose also L in some compact set, I guess. That's yeah. Yeah, that's probably the price you have to pay. Yeah, it was
Okay,
just a curiosity. Yeah, thank you.
so maybe because of time, I think we will finish the question here, but you can see how much interest, Sara, how many questions you had during and after. So people maybe can reach out then separately to you.